Welcome back, everybody. In this video, we're going to breadboard a circuit and write the firmware to control servos, DC motors, and stepper motors with the PIC 18F4550. Let's get started. So before we look at our circuit diagram today, let's take a look at the servos and DC motors and stepper motors that we're going to be using. For a servo motor, on Electronics Express, we're going to use this Parallax. It's actually branded Parallax, but really it's a Futaba servo motor. They're standard servo, and it's only 13 bucks. And this is a pretty standard unit. It has a rotation of 180 degrees. If you use a slightly different servo, that'll probably work too. You might have to make some adjustments to the timing in the servo function in software, but we'll get to that later. For DC motors, we're going to go to Servo City here. Definitely an excellent site. I recommend you check out Servo City if you haven't been there already, if you're interested in purchasing motors of any kind. Specifically today we'll be using this 101 RPM gear motor. It's branded as a 12 volt direct current, but really you can feed it a little bit less than that. It'll still work well for you. I like these motors a lot. They have these nice 3 screw holes here so you can mount these to a flat surface. They're a little on the pricey side, 25 bucks each, but you get what you pay for, and this is a quality part, so this will work real well for us today. If you have any other 9 volt, 12 volt DC motor, you know, that would work also. And here's the stepper motor that we're going to use today rather. Pretty much any bipolar stepper motor will do. Specifically on Electronics Express, we'll be using this part here, 29STP9. These are extremely economical. They're only $4.50 each, but don't let that fool you. This is a quality part. These are definitely some nice motors. You can feed them from 9 to 12 volts. We'll feed it 9 today, or a little bit more than that. That'll work well for us. If you have a different bipolar stepper motor, that'll also work. One thing to beware though is bipolar stepper motors are generally going to have 4 wires in the connector, and if you have a different bipolar stepper motor, your colors of wire might match up differently, so you might have to make some changes in either software or hardware to accommodate that. But if you go with this 29STP9 with the stock hardware and software we're going to go through today, then it'll work great for you. Now let's get to the circuit diagram. Before we take a look at the circuit diagram, let's take a quick look at how we're going to drive some of the motors that we'll be using today. This is the data sheet for the Parallax standard servo, and if we scroll down a few pages, for those not familiar with driving servos, they're relatively simple to drive. You really only have 3 wires on the servo, white if it's a Futaba servo, or that'll be yellow if it's a high-tech servo. That's the control wire, and then red is power and black is ground. Note that it's recommended to use a separate power for the servo motor and the chip. The reason is that you can get a lot of noise on the servo motor power line, and it's preferable to have these separated so that that noise doesn't backfeed into the microcontroller. And if we scroll down just a few more pages, we'll get to the timing diagram for it. And here's how servos generally work. With most servos that are, say, 180 degrees, it's traditional that you have a 1.5 millisecond pulse high that centers the servo. So, and then you have this wait time in between high pulses. Now you'll notice here it says in order to hold its position, the servo needs to receive a pulse every 20 milliseconds. So in other words, you don't want to wait longer than that. So this wait time here could be 20 milliseconds, or it could be less, say 10, 15, etc. Better a little bit less than 20 milliseconds rather than too long. And then the high pulse, again, traditionally 1.5 milliseconds will center it. So for example, with an 180 degree rotation servo, 1.5 milliseconds will put it at 90 degrees, whereas say a lesser amount, perhaps 1 millisecond, will put it at 0, and then maybe 2 milliseconds will put it at 180. Every servo is a little bit different. When you get a new servo, you definitely want to check the data sheet, but then also you'll kind of have to experiment and code to find out what works best for you to get that full swing from 0 to 180 degrees, or whatever the rotation for your servo happens to be. Next, let's take a look at how we're going to drive our DC motors, and how we're going to do that is with the classic H-bridge built from transistors. So if we type in on a internet search, we type in H-bridge, there's a nice Wikipedia page about H-bridges. Please give this a read if you're not familiar with H-bridges. You can purchase chips that essentially have the whole H-bridge in a chip, actually 2 of them usually. But if you use these chips, you have to have wires crisscrossing every which way. Personally, I find it easier to simply use transistors. Another real good source is David Cook's webpage, robotroom.com. Specifically this article here, Bipolar Transistor H-bridge Motor Driver. Honestly, David Cook is a really good author, and he explains this much better than I could. So if you're unclear on H-bridges or you haven't assembled an H-bridge before, definitely give this page a read. And this is the circuit that we're going to be using today. And there's some nice explanation here, and on the subsequent pages, some comparison using different types of transistors, which can be slightly more efficient in some cases. And as long as I'm here, I should also point out that this book, Intermediate Robot Building, contains a number of chapters that provide some circuits for motor driving. Again, if you're a little bit unclear about H-bridges, definitely purchase this book, give it a read, very good. And for information on driving stepper motors, I'd recommend referring to the following webpage. Driving bipolar stepper motor, third search result, this piclist.com page, driving bipolar stepper motors. This is an excellent explanation on driving bipolar stepper motors. Describes the full step sequence and also the half step sequence, although we'll be using the full step sequence today. You do need 2 H-bridges to drive a bipolar stepper motor, so we're going to have 1 for each DC motor and then 2 for the steppers, so 4 total. And this article has some more diagrams. With bipolar stepper motors, there's going to be 2 coils inside the stepper motor and 4 wires. And the coils are sometimes referred to as A and B. That's how we'll refer to them today. So one end of the A coil would be the A end, and then the other end would be the A prime end. And then for the B coil, one end would be the B end, and the other end would be the B prime end. And once you've named the ends, then you can apply the stepping algorithm, either half step or full step, to your stepper motor. So, for example, this tutorial here shows coil A. They're calling the ends plus and minus or off instead of A and A prime, and then they're calling the B coil plus, minus, and off instead of B, B prime, and off. But it's the same idea. We'll use A and A prime. I just happen to think that's a little bit of an easier way to present the information. But in any case, if you're not familiar with driving bipolar stepper motors, definitely check this article out. It explains it very well. Highly recommend it. And now we've got to our electrical diagram. Here's the diagram for the entire project. Actually, I had to break this into 2 pages. This is 1 of 2, and here's 2 of 2 with the H-bridge on it. We'll get back to that in a moment. So let's take a quick tour of the pins, starting with pin 1 and then rotating counterclockwise. We're going to have a potentiometer, only 1 in this project, and that'll be for controlling the angle of the servo. Then for the DC motors, we're going to have a left forward switch, right forward, left reverse, right reverse. And then for the stepper motor, we're going to have a step counterclockwise and a step clockwise switch. We're going to have 3 LEDs here, LED 2, LED 1, and LED 0. At the moment, the way the software is written, they don't do anything, but if you prefer to use those to signal entering a certain motor routine or for debugging later on, they are there and available for use. We're going to use the external clock. We have a 20 megahertz oscillator here, 22 picofarad capacitors to match. Of course, we'll use the 18F4550's internal phase lock loop to up this frequency to 48 megahertz for the CPU clock speed. And next you're going to notice the USB capacitor on pin 18 and the USB connector over here on pins 23 and 24. In a future video, we're going to add USB functionality to this project. So rather than having to do 2 different circuit diagrams and then breadboard 2 different circuits, you can simply put the USB connector and capacitor on your board at this time if you have those handy, and then that way when we get to the future project you won't have to redo the board at that time. So here then next we get to the 4 H-bridges. So I've numbered them 1, 2, 3, and 4, and the 4 wires that effectively go into each H-bridge. If you think of each H-bridge as a separate component, we've labeled D, C, B, and A. And in the center of each H-bridge where you connect to the motor, you're going to have this 2-pin connector. So for the DC motor, they're going to be black and red, and then red and black. And then for the bipolar motor, with the particular motor we're going to be using, the colors are going to be purple and blue for the A and A prime coil, and then yellow and orange for the B and B prime coil. If you're using a slightly different bipolar stepper motor, you might have to experiment with your motor a little bit to figure out which colors correspond to which pins. But ultimately, bipolar stepper motors are generally going to have 4 wires because they have 2 coils. So ultimately, it would be possible to work out a correlation even if you have a slightly different motor. And moving upward here, we have the servo connector. Again, the servo wiring is very, very simple. You have the one control wire that goes to a pin on the chip, and then you have your power and ground, and then here's the programming header. One of the things that we should point out here is that there's 3 different power buses in this project. There's the 5-volt servo power, and then the 5-volt chip power. We definitely want to use separate power buses for the servo versus the chip voltage. That will keep the noise that the servo motor makes away from the chip and will not disrupt the 18F4550's internal logic. So on this diagram, for each of the 4 H bridges, we're going to duplicate this H bridge section here 4 times, and this is the classic H bridge: 2 PNP transistors, 4 NPNs, resistors to match, and then 4 diodes to prevent damage from the inductive spike from the motors when they're turned off. And then also we're going to have 2 regulator circuits here. We're going to use the classic 7805. We're going to take in our 9-volt supply. You could use either multiple 9-volt batteries in parallel, or if you have a nice bench power supply, you could set it to 9 volts or slightly higher. And we definitely want to use the 7805 to feed the servos 5-volt power. Actually, to simplify our board today, rather than having a true second power supply, we're simply going to use the PIC kit 2 or PIC kit 3 if that's what you have to power the chip, and then we'll use only a single 7805 power supply circuit to power the servo motor. Here's at least one possible way to breadboard the circuit just shown. You can use a different way, if you have certain preferences, but at least this is the way that I got it to work for me. Of course, there's no way around the fact that the 4 H bridges are going to take a lot of parts. In this particular case, it seemed to work best to do 2 of the H bridges on this one separate board, and then the other 2 on this extra small breadboard, and those drive the 2 DC motors there. And then this separate 2 H bridges on this separate perf boarded circuit drive the stepper motor. There's nothing wrong with these motors. The tape's only on there to be able to tell the direction that they're rotating. And then on the main perf board here, we have the 6 switches for the left forward and reverse, right forward and reverse, and stepper motor clockwise and counterclockwise. And again, there's really no way around the fact that you're going to have the wires cross a significant distance. There's our 7805 regulator chip and our 5-volt supply there going into the servo motor connector, and there it is leading to our servo. We'll get to that later. And the power supply is going to be used for 9 volts or a little bit more, and the PIC kit 2 is going to be used for the 5 volts for the chip. And coming off the 9 volts from the power supply, we go to the 7805 regulator, and that feeds into the separate bus there that goes to the servo. So there's our completed circuit. So now that our breadboarding's done, but before we jump into our firmware, let's take a quick look at our stepper and servo motor, timer, and interrupt calculations. So we're going to be using the 48 megahertz CPU clock, and again that comes from the 20 megahertz external oscillator, but with the phase lock loop inside the 18F4550 kicking the frequency up to a full 48 megahertz. And also bear in mind the 18F4550 uses 4 cycles per 1 instruction. So for the stepper motor, what would be preferable is about 3 times a second for the stepper motor to make a step. That way you'll be able to actually see the discrete steps of the motor. So it'll clearly be different in its motion than the DC motors will be, which of course don't move in discrete steps. So how we can achieve this time is we're going to take our 48 million cycles per second and multiply that by 1 instruction per 4 cycles. Cycles crosses out, of course. And then we have 12 million instructions per second. And if we use the 64 prescaler for timer 0, then that's going to give us 187,500 divided by 2 to the 16th, because we're going to use the 16-bit option for timer 0. And that's going to equal 2.861 number of times per second that timer 0 will roll over. So if we do 1 divided by that 2.861, that tells us that the timer 0, in other words the stepper interrupt, will occur every 0.3495 seconds. Now for the timer 1 calculation for the servo, we'd like that to happen substantially more often. So recall from the data sheet earlier that we're going to want to send a pulse to the servo at least every 20 milliseconds, if anything more often than that. So to play it safe, we'll send one about every 11 milliseconds, and here's how we're going to achieve that. Again, we have the 48 million over 1, and then 1 over 4 gives us 12 million instructions per second, and we'll use a prescaler of only 2 here, gives us 6 million, divided by 2 to the 16th, because timer 1 is always 16-bit, and that gives us 91.55 times per second that timer 1 will roll over. So if we do 1 divided by the 91.55, that gives us 0.0109. Alrighty, so now we're to the firmware. So our program is going to be called 18F4550 Motor Controller 4.c, and the chip config settings, these are directly out of the external Blink program from a few tutorials ago. You can simply copy and paste those, and then we can move on down to our includes. We only need 3 includes: 18F4550.h, timers.h, and delays.h. And these defines will help us out as far as naming the pins during the rest of the program. So rather than having in our motor functions, port B bits.rb2, port D bits.rd6, and so on, if we simply introduce some define statements to rename the pins at the beginning, that'll be helpful. So we start with our inputs, and then we move on to our outputs, and there's our switches, servo control pin, all the H bridges, and our 3 LEDs. And we're only going to need 2 global variables in this program, both related to the stepper motor, one being stepper motor direction, so that's 0 if the stepper motor is stationary, 1 if it's moving clockwise, 2 if it's moving counterclockwise, and then stepper position. So what stepper position is all about is, if we take a look at our full step algorithm here, there's essentially 4 states you can be in: 0, 1, 2, 3, and then back to 0. And to go from each state, you need a different command. So for example, to go from state 0 to 1, you're going to command the A coil to A and the B coil to off. To go from state 3 to state 0, you're going to command the A coil off and the B coil negative, or in other words, B prime, and so on. And if you're going to go the other way around, if you're going to go counterclockwise, for example, if you're going from state 0 to state 3, then you would command 0 and B prime just the same. So following this table here will be able to take you going down the table if you're going clockwise, or going back up the table if you're going counterclockwise. So to keep track of which state you're in, that's what we need this stepper position global variable for. So we can reference this, and then we can decide what the next step will be. Also including knowing which direction we're moving in. Next, let's take a look at our function prototypes. If you're familiar with the previous tutorial on interrupts, the high ISR and your high priority interrupt code functions will look very familiar. Those are exactly the same starts to those functions as in the previous tutorial. And then we're going to have 3 more function prototypes, 1 for each of the motor types: servo control, DC motor control, and stepper control. You might hear there's some fireworks going off in the background. It's July 4th here in the United States. So there's, at least in terms of sound, there's a little bit of a fireworks show going along with this electronics tutorial. I hope you're enjoying it so far. And continuing on here, the high interrupt vector, again, this is the address in the PIC 18F4550. This 8, that's where that magic number comes from. You're always going to include this, and that way the chip will jump to this function, and then this one assembly statement, your high priority interrupt code, will then jump down to the actual function here where you write your true interrupt routine. So for both the stepper motor and the servo motor, the strategy is pretty much the same. We check the applicable timer interrupt flag bit, that's what IF is short for. If that's 1, for example, we're going to use timer 0 for stepper control. So if the interrupt flag bit is 1, then we reset the interrupt flag bit so that the interrupt can be flagged the next time around, and then we call the appropriate function, either stepper control or servo control. And at the end of these interrupts, make sure you include pragma code. That way it will end the code ending at, or starting rather, at these special addresses. So then when you put pragma code at the end, it goes back to, the compiler goes back to its usual addressing as you continue on into main. So main is relatively straightforward. Again, reference the previous tutorials if any of these statements are unclear, but basically the strategy is turn all the timers off until we fully configure them to prevent activities from happening before we've had a chance to configure the timer that we don't want to have happen yet. Then using the tris registers, we're going to configure our input pins and our output pins, again with the tris registers. And then we're going to init all of our output pins to off, so again we can use the names from those pound define statements we had earlier rather than referencing the pins specifically from this point in the program on. So we have our servo control pin, our 16 H bridge pins, 4 each for 4 of the H bridges, gives us a total of 16 H bridge pins, and then we have our 3 LEDs which can be used for debugging. Then we have our analog to digital configuration stuff. Please consult the second tutorial series on the I/O demo board if you're a little bit new and would like to get up to speed on analog to digital conversion with the 18F4550. These these settings that we're using, we're going to use AN0 as our analog input channel, and that potentiometer, as it's changed, will be read in, and then we can use that to command the position of our servo. So moving on, once we're done with the analog to digital conversion configuration, then we're going to set the I pin and the GIE, GIH bits to 1, and that's going to enable priority levels on interrupts, and then that will also enable high priority interrupts. And then we're going to configure timer 0 and timer 1. Again, these are relatively standard timer settings. Please reference the previous video on timer configuration. And once we're done configuring timer 1, then we're going to turn timer 0 and 1 on. And at that point, we'll simply enter an endless while loop. Now, it looks like we're only calling DC motor control because that's all that we're calling directly, but of course, bear in mind that the interrupts are going to call the servo and stepper functions when they're flagged every so often. So next, let's take a look at our 3 motor control function. Recall from the calculations earlier that this is going to run about every 11 milliseconds. So when our function starts, we're going to declare 2 integers, I and servo delay, and then we're going to start the ADD conversion, and then we're going to wait here until addcon 0bits.go done does not equal 1 any longer. At that point, the conversion is complete, and then we can read address H, which of course is an 8-bit register. So, for example, at the smallest, address H is going to be 0. At the largest, it's going to be 255. So let's take the largest case of address H, for example. So that's going to be 255 divided by 12 times 30. And then casting that to an integer is going to be 637. So then we're going to come down here and actually pulse the servo control pin high. And what we're trying to do with that is, if we have a 1.5 millisecond pulse, that's going to set the servo to 90 degrees. And if we have a 1 millisecond pulse, that's going to set it to 0, and a 2 millisecond pulse will set it to 180 degrees. So the idea is the potentiometer read in through address H, we're then going to have to take that, and using this line here, where servo delay is assigned, we're going to try and translate that via this for loop into an actual time delay that corresponds to these times. So let's go back to our example where address H was 255 and therefore servo delay was 637. So we're going to loop from I is assigned negative 135 while I is less than servo delay. So in other words, we're going to loop 135 plus 637 times. So we're going to loop at absolute most 772 times, and that's going to set the servo to 180 degrees. And the reason that that's going to happen is when we're in this loop, we're calling this delay for 10 times TCY amount of time. Again, for explanation on TCY, please see the previous tutorials covering delays. But to quickly summarize, TCY with the 48 megahertz clock speed that we have is going to be 0.083333 microseconds. So the delay that the 10 TCY line is going to have is going to be 0.83333 microseconds per iteration times the number of iterations we're doing, which is actually times servo delay plus this 135. Because, for example, now let's take the lowest possible case. Let's say address H is 0. In other words, the potentiometer is turned all the way down to 0. Well, 0 divided by 12 is 0 times 30 is 0, so servo delay is also going to be 0. So then we're going to come down here and we're going to run through this for loop 135 times. So in other words, we're going to run through this for loop at least 135 times. That's going to correspond to a 1 millisecond delay or 0 degrees. And at most, we're going to run through it 772 times, and that's going to correspond to a 2 millisecond delay and 180 degrees. Now, these numbers don't necessarily translate exactly, and with servos, you have to do this. To some degree, it's a trial and error. When I first went through these, I calculated what I thought the numbers should be, and it came out close. But then what you're going to find is that you have to adjust the minimum number of times and then also the maximum number so that your particular servo will work. So once we've looped the appropriate number of times, then we're going to turn the servo control pin back off, and then at that point the pulse is complete. So next, let's take a look at our DC motor control function. Remember, this is the one function that is actually directly called in the infinite while loop rather than called through an interrupt. And this function is really very simple. Remember, the switches here are all logic low. So, for example, if the left forward switch is off, remember 1 means off, and the left reverse switch is off, that means we're in left motor coast. If the left motor forward switch is on, and again 0 is on, and the reverse is off, that means we're in left motor forward. So then we command the applicable H bridge appropriately. So for example, to go forward, we're going to command the H bridge pins B, C, D, C, B, and A rather to 1, 0, 1, and 0. And again, please see the previous section with the circuit diagram, and that'll clarify how we polarize one side of the H bridge. Well, actually, let's go through an example. So for example, the DC motor is on H bridge 1, or actually the DC motors, I should say, 1 is on H bridge 1 is on H bridge 2. So for example, let's say we're commanding H bridge 1. If we power pin D and B, and then we jump over to the H bridge diagram, well, what's that going to do? Powering D is going to turn this transistor on, and therefore this transistor, and powering B is going to turn this transistor only on. So what that's going to allow current to do is flow in here, through the motor. Note we're going this way to the right as we're looking at this diagram, and then through this transistor. If we did it the other way around, so therefore the current's going that way. If we did it the other way around, if we powered C and A only, then A being powered would power this transistor, which therefore would power this one. So, and also remember we're powering C. So then current would come in here, through here. Now notice it's going the other way, to the left as we're looking at the illustration, and then it's going to go through here to ground. So that's a strategy for how the H bridge actually translates into motor control in this function. So we can command both the left motor and the right motor to go forward, in reverse, or coast, or electrically brake. And now moving on to the stepper function, the first thing that we're going to do is we're going to check the stepper switch to see if we're in clockwise or counterclockwise direction, or otherwise we'll set the global variable direction to off, being 0. So then we're going to check our direction. If stepper motor direction is 0, then we're not stepping either way, so we can simply return from the function. And if stepper motor direction is 1, so we're stepping forward, or in other words clockwise, then we're going to command H bridges 3 and 4 as applicable. So for example, if we're in stepper motor position 0, and again we'll reference the table back at the beginning of the program to determine our state. So if we're in state 0 and we're looking to move into state 1, then we're going to, with the A coil, we're going to command that to A, and the B coil, we're going to leave that off. So back to where we were here. So if stepper motor position is 0, then we're going to command A and then the B coil to 0. If we were in stepper position 2 going forward, looking to get to position 3, for example, then we would command the A coil to A prime and then the B coil to 0. And here's the applicable commands to command the coil. So for example, for the A coil, H bridge 3, we're going to command to 1, 0, 1, and 0. Whereas for example, A prime, we would command the A coil, which again is H bridge 3, to 0, 1, 0, 1. And then we'll make the applicable matching commands for coil B. And then we're going to have our second big set of if statements here for if the stepper direction is 2, in other words, if we're stepping counterclockwise. So this section is going to look very similar to the previous section, but again, bear in mind, going back to our state table at the beginning, now we're working back up the table. So for example, if we're in state 3 and we're going backwards, then to get to state 2, we're going to have to do, for example, A prime for the A coil and 0 for the B coil. So we'll change our statements here applicably. And that completes our program. Of course, each time, one last note here, for no matter which way we're stepping, well, if we're stepping clockwise, then we're going to increment stepper position, the global variable, positively, and if we're stepping counterclockwise, we're going to decrement stepper position. And stepper position, of course, is going to count 0, 1, 2, 3. So if we're counting up and it gets to 4 or greater, then we have to return it back to 0. And if we're counting down and stepper position gets to -1 or less, then of course it should never get to less than -1. Really, we could put that statement there as equals -1 either way. In any case, then we have to reset stepper position back to 3, so we can go back to 3, 2, 1 again as we continue through. And that completes our program. So let's go ahead and compile it and load it and give it a test. Alright, so we've gone ahead and compiled our program and loaded it in, and let's go ahead and give it a test run. So here's the left motor forward and right motor forward, and again, because we're doing this with interrupts, we should be able to use all the motors simultaneously without any problem. And let's take a look at the stepper. And there's the stepper going counterclockwise and clockwise. And let's go ahead and command the motors in reverse. So we're going coast mode for just a second. And there's reverse. And let's go ahead and use the potentiometer to adjust the servo. And that's working real nice. There's our nice 180-degree sweep. We can command to any position successfully, so that's working great. And all the while the stepper's still moving, DC motors are still moving, everything's multitasking for us real nice. Looks like definite thumbs up. Congratulations! You now know how to control servos, DC motors, and stepper motors with the PIC 18F4550. Here are some upcoming videos. An updated USB demo board, including a more modular design, and also rather than showing the finished product only as the previous USB demo board did, we'll walk entirely through the process step by step. Therefore, that in conjunction with the more modular design will allow you to be able to add USB functionality to your microcontroller projects very quickly and easily. After that, we'll take a look at an 18F4550 USB motor controller with C# post software. So in other words, essentially the same functionality that we saw in this tutorial today, but instead of commanding the motors via switches and potentiometers on the board, we'll have a nice C# front end on a host computer to perform the motor commands. After that, we'll take a look at redoing Tracker from the OpenCV tutorial series, but with a pan and tilt platform for the webcam controlled by 2 servos, so that rather than simply updating a certain area on the screen where Tracker is able to determine where the object is, Tracker will be able to command the camera to pan and tilt around the room to track the object that it's focusing on. So there's some interesting things to look forward to, and I'll see you